Good day, everyone. So welcome to the week number 11 of our ECE 6171 or Fundamentals of uh, Mixed Signals and Sensors. So for this week, our topic is Data Converter Fundamentals. Okay. So for the learning outcomes, okay, so by the end of this module, the student is able to, number one, define signal processing and its components. Number two, understand the conversion patterns and its categories. And number three, analyze signal processes. Okay, so this will be the topics that we will cover for this week. Signal processing, signal conversions, quantization, gain, offsets, and errors, and then bandwidth. Okay, so as usual, I will all this one. I will jump from the presentation to the module from time to time for a better explanation. Okay, so let's start with signal processing. So signal processing is defined or is usually more efficient, robust, convenient in the digital domain. Okay, uh, it is the need to convert to and from analog to interface with the world. Okay, so what does this mean? Usually, the signals that we are taking or we are getting from real life data is in the analog form. But of course, since we are gonna use those information and analyze this information, usually the analysis happens in the digital form, in our computers, in our microprocessors. Okay, so the analog signals that we are getting or we are collecting from our whatever we are trying to measure or what we are trying to sense, okay, will be converted to digital form. Okay, so this is how a signal processing usually looks like. So we have filters, analog to digital converter, digital signal processing, digital to analog converter, and then reconstruction filter, and then output. Okay, this is the signal flow. Usually, again, input, filters, analog to digital converter, digital signal processing, digital to analog converter, and then output. All right. So digital or rather data conversion accuracy limits system performance. So in-depth understanding of data converter performance is important in many applications. So we will start with digital to analog conversion. So a digital to analog converter or DAC is a device which converts a digital word to an analog voltage. Okay, again, digital data comes usually in binary 101010. The function of the DAC or digital to analog converter is to convert the digital signal to analog. Okay, so we have here the voltage out is equals to the reference voltage times this one. We will discuss this later more. Okay, this refers to the bits of the every bit of the data. So reference voltage or VREF is typically generated by a bandgap reference. So we want each bit to represent a fixed voltage. Okay, so LSB means a least significant bit, if you're still familiar with it. Okay, so that is usually, or rather the voltage of the least significant bit is the reference voltage over 2 raised to n. N is the number of, or the resolution. Okay, again, n is the resolution. Resolution means the number of bits of a data. So I'm sure you've heard of the term bits. Okay, for example, if you have a 1010 data, so it is made up of 4 binary numbers. So this is 4 bits. Okay, so every number or a group of binary numbers depends on how many digits are there. Okay, so that is the solution. We relate many performance metrics to the unitless least significant bit. Okay. Okay. When we say least significant bit, hopefully you're still familiar with it from our codes, logic gates, the logic gates course. Okay. For example, if we have this data, 1, 2, 3, 4, 5, 6, 7, 8. Let's have 1 in here. Right, so let's refresh ourselves in conversion from digital to decimal. This is 1, this is 2, this is 4, 8, 16, right? 32, 64, and then 128. Sorry, 128. So to convert this one, so we have 128 plus 32 plus 16 plus 8 plus 2 plus 1. That is equal to 160, 170, 186, 187. Okay, 187. If we convert this to decimal, but in this binary number, the least significant bit is usually the lowest valued bit. In this case, 1. Okay. Why? Because in conversions, in digital to analog conversion or analog to digital conversion, we usually expect errors because there is no perfect system to convert digital to analog system. There will always be an error. Okay. So the role of significant or the LSB usually is this one. If this bit will be error. For example, instead of 1, it becomes after the conversion from analog to digital and then digital to analog. Instead of 1, it becomes 0. Okay, so if this becomes 0 and we convert it to decimal, it becomes 186, right? So as you can see, the damage to the value is minimal. But if this bit will be error, for example, instead of 1, this becomes 0. So instead of 187, the value now becomes how much? 59. Okay. So the error is very, very large. Okay. So usually the least significant bit is the what do you call this one? Gets the least importance in the conversion because even if it becomes an error, the error is still minimal. So that's why you will always encounter the LSB. The power of the conversion, I'm saying power, but I'm not referring to watts. What I'm trying to say is how accurate the conversion is depends on if it can accommodate the LSB or not. If it can ensure that the LSB will have a correct value. Okay, so there will be conversions in which the LSB is almost rejected, but there are also conversions that the LSB is given importance. Okay, so that's the measure of the accuracy of a converter. So anyway, let's proceed. So here are some digital codes. Okay. When we say digital codes, how do we represent our digital code to voltage form? Okay. So let's start with unipolar. If we have unipolar, for example, let's go here. Unipolar. Okay. For example, we have the signal. Unipolar means it can only be either positive or negative. The value is positive or zero, or zero and negative. So what does this mean? For example, this is 4 volts. The maximum amplitude here is, or the maximum voltage is 4 volts. So we will divide this voltage into 2, okay, which is 2 volts. Okay. In this case, all voltages below 2 volts will be, for example, we will take this one. When converted to digital, they will be treated as 0. Then all of the voltage above 2 will be treated as 1. Okay? So that's what we mean when we say unipolar. So if we will sample this signal, for example, we have this division of time. Let's say this is 0.1 seconds, so 0.1, 0.2, 0.3, 0.4, and so on. So if we will write the signal in digital form, this will be 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0. When we write this into digital signal using voltage, okay, so the magnitude will only be 2, maximum and minimum. So let's say the maximum is 4, minimum is 0. So all of these zeros will be 0 volts. And then all of the ones will be 4 volts. So it will look like this. Which, if we will compare to our signal, it is not accurate. So that's the problem with unipolar. It is very simple, but the accuracy is very low as well. Okay? So this is for our unipolar. Next, we have sign magnitude. What's the thing with sign magnitude? For example, sign magnitude. Wait. In sign magnitude, for example, we have 1, 0, 1, 0, or 0, 1, 1, 1. When we convert a digital signal or a digital code like this one to digital waveform, so this is not limited to only 2 values. Okay, what happens here is, for example, wait. The maximum voltage is 4 volts. No. Let's do 8 volts or 7 volts. We will be making use of the negative as well in sign magnitude. Okay, and then what happens here is the first digit will be used to determine the sign that will be used. Okay, so for 1010, let's say ones will be used to indicate negative, zeros will be used to indicate positive, depending on the system, of course. And then the rest of the code will be used to identify the magnitude. So since this is 0, 1, 0, this will be equal to 2, right? 1, 2, and 4. Okay. In the case of 0, 1, 1, 1, this will be, or the magnitude will be equal to 7. 4 plus 2 plus 1. This will be positive. This will be negative. So 1, 0, 1, 0 will be equal to negative 2. Okay. So this is negative 2. While 0, 1, 1, 1 will be equal to positive 7. Okay. So this is for sign magnitude. The thing with sign magnitude is this is more accurate than unipolar, because if, for example, we will convert this one, every time sample will be for bits. Let's say this will be 0, 0, 0, 1. This will be 0, 0, 0, 0, 2. If we will trace this in a if we will trace this here, since there is magnitude, okay, so it will not just be a single, this will not only be of two values, maximum and minimum. So it will have many values as well. Okay. And the sign matters. So if the signal has a negative part like this one, so it will also be counted in the conversion to the digital signal. Okay. So if we will trace this one using sign magnitude, more or less we will be taking this type of signal, but it will be digital form, of course, which is now more accurate to the original signal. Okay, so that's the difference between unipolar and sign magnitude. For one's complement, this is just a step one. Ones and twos complement are usually step ones. Same with offset binary. They have bigger applications, but just to give you an idea, if you have no idea yet what is ones, twos complement, and offset binary. For example, we have a value of 1, 0, 1, 0. The ones complement of 1, 0, 1, 0 is just the complement of each bits. Okay, so the ones complement will be 1 or 0, 1, 0, 1. Okay, so this is the ones complement of this. The twos complement is, okay, ones plus 1. Sorry, it looks like the first one. The ones complement plus 1. That's the twos complement. So, for example, the ones complement of 1, 0, 1, 0 is 0, 1, 0, 1. So the twos complement will be 0, 1, 0, 1 plus 1. Okay, so that will be 0, carry 1. So 1, 0, 1, 1, 0. So this will be the twos complement. Again, ones complement, twos complement, and offset binary are usually step ones of a bigger process, which will be discussed in the preceding meetings. So let's stop with this for now. The offset binary, however, goes like this. When we represent a number, for example, we have a decimal number 7. Okay. When we convert 7 to binary, that will be 1, 1, 1, right? And that is the maximum value. The minimum value will be 0, 0, 0. So if we plot it on a straight line, okay, so this will be the 0, which is the 0, 0, 0. This will be the 1, 1, 1, which is the 7. When we say offset binary, what we do is, instead of just using 0 and 7, we try to shift the binaries to a certain number n. Okay, depending on how many bits. For example, we have 3 bits. So 3 bits, n will be equal to 2 raised to 3 because of 3 bits. So that will be 8. Okay, so what will happen is we will shift our binaries to the left. So the 0 now, instead of on the 0 itself, it will be shifted to -8. So this will be now the place for 0, 0, 0. And the 7, instead of being on 7 itself, it will be shifted by 8. Okay. So instead of being on 7, it will now be on -1. So here is now our 1, 1, 1. So that's for the offset binary. Again, these three are usually step ones of bigger processes. So we will leave it for now on this. Okay. So let's proceed. So ideally, the analog input has infinite precision, analog. But again, there is no ideal system. So the real life applications are usually, number one, limited by noise, and then by distortion. To give an example, when we speak through the microphone, you will be hearing a lot of noise. Aside from the background noise, the microphone itself has interference. Usually that is 60 hertz interference, which is the frequency of our power, household power. Our household again is 220 volts, 60 hertz. So that is being picked up by most of these systems. So there will be filters that will be applied, but of course, the better the filter, the more expensive it will be. That's why when we buy not so expensive materials, we will still be experiencing noise and distortion. Okay. So the output has a finite number of information carrying units. So the ADC, this time we will be talking about analog to digital converter, quantizes the input voltage to a finite number of bits. Okay, so I'll clear this one. Please screenshot if you need to. 5, 4, 3, 2, 1. Okay, so we will go with quantization. So quantization or quantization, however you read that one. Okay, so that is applying quantity or values to certain points of a signal when we convert from analog to digital. So the data converters must represent continuous values in a range using a set of discrete values. So a binary code is used to represent the value. But this time we are talking about analog to digital, just like this one. Unipolar is also using quantization, but again, it only has two values. So this is quantization using two values only. Okay, so that's the problem with unipolar. Let's try to make an example using higher resolution. Let's say we will do quantization with 4 bits or 3 bits. Let's do 4 bits. Okay. Wait. Is it capital N or small letter? Let's go with small letter. So 4 bits. Okay. For example, we have this signal. This one. Very small. Anyway. Let's say the maximum amplitude is 4. So 4 and -4. Okay. So the formula is this one. So x max, that is for delta, minus x min over m. Okay, so that's how we divide our signal. It's kind of hard to draw the proper division. So I'll just make some freestyle drawing here. Please double check on your supplementary materials, since it is hard for me to draw a good drawing using my system right now. Okay. So what happens in quantization is that this point, I'll try to enlarge this one. Okay, so this point will be sampled. This point will be sampled. This will be sampled, etc. So if we will be using unipolar, so we will just divide this by 2. It's 2, just one side. This will be discarded. Okay. Then this will be zeros. This will be. All right. So if we have 4 bits, n is equals to 4, so we will be dividing the signal into 4 parts. Okay. So how do we do that one? We have 4 volts. I think we have a formula here. Don't have a formula here. We don't have a formula here. Anyway, what will happen here is 4 divided by n. Am I doing this right? 3, 4. Anyway, we're just trying to give you an overview of what quantization here. We're not actually doing the actual solving. So let's just try to divide this signal into 4 parts. So this is one part, this is another part, and another part. Okay. So what happens here is all of the values in this area, use another color, all of the values in this area will fall to this voltage value. Then this area will fall to this voltage value. Okay. And so on and so forth. So this, lastly, this to this. So we have 4 voltage levels. Okay. So this one is -4. This one will be -2. This one will be 0. This one will be +2. So all values between -2 and -4, when represented in digital form, will be equal to -4. All values between 0 and -2, when converted to digital form, will be -2. Okay. So if we will draw this one in digital, it will approximately look like this. Okay. So this part will be 0. Sorry. This part will be 0. This part will be +2. This one will be 0. This one will be -2. And then this one will be -4. 4. So the higher the resolution, or the higher the n, the more accurate the signal will be to its analog origin. Okay, so again, this part is 0. This part is 0. Okay, I have not moved this one. Let's try to move this one. So this part was 0, this part is 2, this part is 0, this part is -2, this part is -4, then this one is -2. Okay? So that is what we call quantization. We are not just using two voltage levels, but we will be representing our analog signal with the number of voltage levels equivalent to its resolution. That's quantization. Okay. This is for the time. Okay. This is for the time division, or T. How many samples will we get this vertical sample? So this will be the formula. So X max minus X min divided by M, or M is equals to 2 raised to N. Okay. Number of bits. So in this case, if we will have if we have 4 bits, okay, so X max minus X min, okay, over M, or 2 raised to N. Usually when we design a analog to digital converter, so this is determined, this is determined, this is also predetermined. So we will already know the delta. Okay, and then so that's it for quantization. We have this what we call quantization error. Okay, so what do we mean when we say quantization error? Quantization error is the difference of the actual value to the quantized value. Okay, what do we mean? For example, let's take this point here. Hopefully you can still see this one. Let's take the sample here. Okay, if we will look at the digital signal, it will be somewhere around here. This point. This point. Okay. According to its quantized value, the value is -2. This one. But its actual value, let's say around -1.3 volts. Okay. So there will be a difference between the quantized value, which is -2 volts, and the actual value. In this case, -1.3 volts. The difference between the quantized value and the actual value is what we call the quantization error. Okay? So for every point, as you can see, the quantization error is also changing in value. So from this point, the quantization error is very large, and then it gets smaller and smaller as we reach our quantization value. Okay. Then from this point, this will be the quantization values. The error is large, 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 small, 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 until the error is 0, and then it gets larger again, and this case gets larger again. So that's our quantization error. Next, you have quantization noise. Okay, so this will be the function, or this will be the representation for our quantization. This one. So model the quantization error as noise added to the original signal. So this is the original signal. This is the quantization error. Okay. So you add the error to the signal. So this is the signal that is going in to the system. Okay, again, original signal plus the error or the noise. This is actually the system for all input signals in a system. So the original signal plus the noise, that will be the signal that is going into the system. So we have some assumptions in our quantization noises, quantization noise. So all quantization levels have equal probability. Okay? And then large number of quantization levels or M, uniform quantization steps or constant delta, and then quantization error uncorrelated with input. Let's see if we have some. Yep. So next we have, let's discuss this one first, the probability density function. We will not really go deeper into this, but we will just try to get the idea of the SNR due to quantization noise using the probability density function. Okay. So for the quantization error, as you can see, let's go back here. For this area, okay, so let's take this part. How to do this? What color can I use? Is this one. So let's take this area here. Okay. The upper range of the signals here is -2. The lower range is -4. Okay. So the values of the signal that will fall to the -4 quantized value will start from -2.000000001 until -4. So in this case, if we will place that in a probability density function, so our lower value or lower range will be -4, and then our upper range will be -2 or something like that. Okay, again, we are not trying to solve here exactly, we're just trying to understand the concept of the quantization error using the probability density function. Okay. And if we go back to our this one, let's make another graph. So if we have a signal here, we cannot exactly determine the value at a certain point. For example, this one in an analog signal. Okay, so we are trying to since the analog is continuous, so for every time for every value of time, there will be a different voltage value, okay, for our analog signal. So instead of trying to pinpoint the exact value, we will take an area here and then try to guess the value of this point, which will be in between this area. So this is our X min. This will be our X max, right? Okay. I'll just call this X min and X max. This is y, this is x. So this will be x min. This will be x max. Right? So the possible value of x will be delta x or x max minus x min. Okay. Then the height of this is equal to y. Okay, let's use another color. The height of this will be equal to y. So y, which will be the function. Okay, or let's say that is f of x. All right. Again, delta x is dx. So if we will take the area of this strip, you see where we're going, right? Okay. So the area of this strip will be integral of f of x dx. Because the value of our x will be somewhere inside this strip. We cannot determine the exact value, but we know that it will be somewhere inside this strip. Okay, so that is probability density function. That's why you can see a integral formula in here. It is coming from this principle. Okay, so that's it. And then we have this term we call the SNR. SNR means not the grocery shop. SNR means signal to noise ratio. Okay, so that's SNR. So in simple formula, SNR is equals to the signal divided by the noise. This can be represented using voltage, using power, or other quantities as long as they're the same. And then since the ideal signal should have a zero noise, right? Ideal. So for an ideal signal, the SNR should be equal to infinity, since that will be divided by 0. Okay? That's it. Again, we're not trying to really solve here. We're just trying to understand the concepts behind these terms. Right? So let's proceed. Next, we have what we call the sampling jitter. Okay. The sampling jitter is the uncertainty in the timing of the sampling clock due to circuit electrical noise. Example, white noise or flicker noise. So what does this mean? It means, okay, let's go here. Why do we have this sampling clock? And why do we have this timing? Why are we experiencing sampling jitter? Okay. For example, we have 1 0. 1 0 1 0 1 1 0 0 0 1. How does the system know that there are 3 zeros and 2 ones that are consecutive? How does the system know that it will not count it as just a single zero? Right? If we will plot this in the diagram, we have 1 0 1 0 1 1. Okay, 0, 0, 0, 1. When we transmit data using our electronic systems, we are using time, clock, timing, okay? Sampling time. For example, every bit will last for, let's say, 0.05 seconds. Okay, 0.05 seconds. So if the system counts this as 0.1 second, it will know that there are two ones. Counting this one, 0.15 seconds. So that is 0.05 seconds. So it will know that there are three zeros. Okay, but that is the ideal situation. Again, the system is not ideal. So what does that mean? The system will tick every 0.05 seconds, right? It will tick. For example, it will tick at this time. After 0.5 seconds, it will tick again. After 0.5 seconds, it will tick again. And again. And again. Okay. And again. Oh, we have two ticks in here. Lastly. Okay. So that's for the measurement of every 0.05 seconds. But since, again, there is no ideal system, in practical applications, the time of measurement are not all constant or not all equal. As you can see from this illustration, there will be time that the measurement of or the tick of the clock is of this width. There will be times that it will take up a large width. Okay, this what do you call this one? This an inconsistent timing, okay, will result to errors. Okay. For example, instead of three zeros here, if the clock has, for example, this is a mobile device, and then the device was shaken or moved abruptly, and then the system has been disturbed physically, and so on and so forth. So instead of that very small tick, the clock here made a very large width of time measurement. So instead of measuring three zeros, okay, and on the output, it will now say 10, 10, 11, and only two zeros and one. See the error? Okay, so this is one instance wherein the sampling jitter affects the output. Okay, so let's check this one. So sampling time uncertainty translates to an error in the input voltage. Needs a low noise sampling clock to get high accuracy. You must have heard of the term quartz crystal. Okay. In electric or electronic devices, usually the clocking used is a quartz crystal. Let's see. Let's try to. And this is how it usually looks like. But inside that is a quartz crystal. A quartz crystal will be what do you call this one, will vibrate when supplied by voltage. And then there will be some measurements on how often it will vibrate, etc., using circuit arrangement, using capacitors, inductors, resistors, and other components. Okay, this is an example of a digital clock, a digital watch. Where is the crystal? I think this is the quartz crystal. Not really sure. Or yeah, this is the quartz crystal, I think. So there. Okay. This is fairly accurate. Very accurate. This is the most common used clock in electronic devices. This is not really that expensive and is very accurate for its price. The crystal oscillator or quartz crystal oscillator. Okay, so that's it. That is a good example of a low noise sampling clock with high accuracy. Other electronic clocks that are being used, we have I can't say the word, but it's on my mind for this one. So anyway, never mind. I can say the word. So for our sampling time, we have specifications. We have gain, we have offset, we have integral non-integrator nonlinear, integral nonlinear, differential nonlinear, missing codes, and then monotonicity. Okay, so for the gain and offset, so these are easily corrected, does not limit accuracy, and corrected before calculating INL and DNL. Okay, so this is yeah, it has the same explanation. So this is the ideal, for example, this is the ideal value that we are going for. And then this is the actual gain that we are having. So there will be an offset between the ideal gain and then the actual gain. So the offset is the error. INL or integral non-linearity error measures deviation from a straight line. Okay. So best fit straight line or based on endpoints after correcting for offset and gain error. For example, this is the actual signal. So this is the gain at first. Then after measuring that there is this much error in the gain or there is much offset. So the INL will correct the gain. It will offset the gain here and get a much better output. Okay, so that is the role of the INL. Result usually given in LSBs or least significant bits. So these are static, meaning they are measured from DC inputs. So next we have DNL or differential nonlinearity error. So DNL, on the other hand, is a measure of the step size error. It is ideally the distance between two codes are exactly 1 LSB after the correction, like INL measured at DC. Both INL and DNL are common measures of data converter accuracy. Okay. Next, we have monotonicity and missing codes. Monotonicity is applicable to digital to analog converters. Increasing the input code should always increase the output voltage. Severe nonlinearity will cause the output to decrease when the input increases. So missing codes in ADCs when an output code does not occur for any input voltage. Settling time and finite speed is also important to consider. Next, we have effective number of bits. So data converter resolution is the number of physical bits in the system. The effective number of bits, or ENOB, tells us how many of these bits contains useful information. So relate the data converter performance to a converter limited only by quantization noise. Okay. Just to give you an idea again, like how we discussed the LSB earlier, or was that? Oh, it's not here. So anyway, for example, we have this number of bits. Not all of the bits are useful in the system. For example, this one. Let's say these are the only useful bits. So NOB, the rest will be LSBs. Okay. So that's how usually the system goes. Synad is signal to noise. What is AD again? Signal to noise and deviation. Okay, signal, I'll confirm. Synad. I think this is signal to noise and deviation ratio. And distortion. Okay, so signal to noise and distortion ratio. So this is the formula for ENOB. Synad minus 1.76 dB over 6.02 dB. Anyway, the next we have the figure of merit. Let's see if we have something that we've missed. Okay, so none. Figure of merit. Try to come up with an equation that tells us how good the data converter is. So several possibilities or several equations have been made, but the most common used is figure of merit, or FOM. So the formula for figure of merit is equals to P over 2 raised to effective number of bits times F of N. Okay. So this is not necessarily a fair comparison, but it tells us that if we want 1 bit improvement, so we should expect the power consumption to double. Okay, the next or last, I think this is the last one. So we have the effective bandwidth. So the effective bandwidth tell us the frequency where the synad is 3 decibels lower than the best case value. Okay, so that's it for our week 11 discussion of our fundamentals of mixed signals and sensors. Again, the topic is data converter fundamentals.